What about COVID-19 reactions, right? So any sort of adverse response takes a long time to recover and all that, right? So what's the CV of response or recovery time? So while different countries conducted the vaccination exercises kind of differently at different times with different um vaccination brands and companies, right? So how do we compare these fluctuations? Again, coefficient of variation. So you see that this notion of standard deviation, quote and unquote, per unit mean, I think I put it down here, right? So it's the best way to understand what CV is all about, and that there are plenty of users, especially all the more when we are interested to compare standard deviations across, somewhat different measurements. And I give an example here that is so drastic that we even have different units, distance versus dollars, right? And you can even ask that question, right? Okay, so that's coefficient of variation. Next, we want to talk about Z-score. Z-score, instead of applying a Z-score towards the whole bag of data, we're going to ask, what's the Z-score of this piece of data? So you see, the way we use Z-score is different. We ask, what's the Z-score of this data value X? So calculation, very simple. Just apply X minus the mean of the bag of data over the standard deviation of the bag of data. Okay, so of course the standard formula uses population and uses population mean, population standard deviation. So that's the definition. Occasionally, right, and as you can understand, a lot of the real life experiments, surveys, census, studies, research, analysis, data collection are oftentimes a subset of the big problem that we are trying to study. So oftentimes, actually no one can know the mu and the sigma precisely. Sometimes by the time we actually know the mu or very close to it, mu has changed again. So it becomes a very difficult formula to apply if we insist that it has to be mu and sigma all the time. So even though technically we write x minus mu over sigma, a lot of times we also substitute an estimate of mu with x bar. So don't be surprised to find people calculating Z-score using x minus x bar over s as an estimate or a good estimate of sigma. So the calculation being made here, let's understand why we also want to define Z-score. So Z-score, think of it as a unit conversion, is probably going to be very helpful here. So instead of talking about the stock price, 25 cents, 30 cents, sorry, $1.95, $1.05, we talk about the Z value, the Z value. So Z value will then be converted to 0, 0.1, negative 0.5, 1.2, 0.1, 0.3, negative 0.4, yeah, something like that. So when it's exactly 1, it will be 0. When it's exactly the mean value, because then mu minus mu is 0, right? So Z-score will always be 0 whenever the measurement is exactly at mu, the population mean. So all numbers, all measurements, all bags of data, their Z-scores individually for the data, right, will always be 0 when that measurement is exactly on mu itself. Keep that in mind. There's a very kind of a distinctive nature of Z-score, right? So all measurements can be converted to Z-score, whether it follows normal distribution or not. Because all you need is the population mean, which exists. All you need is the population standard deviation, which can be calculated. So long as you have these two numbers, you can calculate the Z-score for each measurement, even though as a histogram, the data doesn't look like a bell curve at all. No problem, right? So don't worry about that. Just what's the Z-score of this value? So think of it as a unit conversion. We want to discard the unit, and we want it kind of recalibrated in such a way that whenever the data measurement is the same as the population mean, then the Z-score is 0. And as a result of dividing by standard deviation, we can interpret Z-score as the number of standard deviations away from the mean. So starting at the mean, when you have fluctuations, positive ones, one step means one standard deviation. And as you can probably just have a feel of it, different data sets will have its own kind of like a stride. That means when you take one step forward, how large or how small is that step? Everyone has their own stride, right? So every set of data has its own stride in that sense. So when we experience fluctuations in the measured data, positively or negatively, Z-score will correspondingly be positive or negative. And when Z is 1, it's always exactly one standard deviation to the right of the mean. And then if Z-score is 2, 2 standard deviations away. If Z-score is 3, 3 standard deviations. So taking our airplane and stock price, if the SD of airplane is 50,000, all right, so at the mileage 250,000, Z-score is 0. At the mileage 300,000 kilometers, Z-score is 1. At the mileage 350,000, Z-score is 2. And of course, at the mileage 200,000, Z-score is -1. That's right. And of course, you can have fractional Z-score, right? So half a standard deviation away. So that would be 275,000 kilometers. Then your Z-score is 0.5 plus 0.5. So what's so interesting about converting the data measurement to a unitless value called Z-score? Z-score has got a very well, you might find it peculiar definition here, more because you want the offset, you want the C level, you want the 0 level, the reference level to be at the mean. You want the stride, right, the maximum and the minimum, how wide or how narrow, to be adjusted based on how large or small the standard deviation is. So when you do that, suddenly the maximum or minimum of Z-score cannot be too large or too small. Okay, so because if the data fluctuates a lot, then SD is large and Z-score is correspondingly divided by a large number and becoming a small number. So any set of data, no matter how wild or how little they fluctuate, your Z-score cannot get beyond 3 and -3. So in absolute value, it cannot go beyond 3 most of the time, right? So if it does burst this 3, whether it exceeds 3, 3.5 or negative 4.1, then those values are so extreme as to be called outliers. They are either to be discarded because they are random noise, or they are super interesting because that's like alien message, finally we found it, right? So that is how interesting things are detected when you convert to Z-score. Yeah, because if you tell me the airline, mileage is this, one would actually has to be an airline expert, right? You need to have a lot of domain expertise to understand whether this number is large or small. But when we're doing statistics, we're good with numbers. We're not necessarily good with the domain expertise. So even though we are not airline or air industry trained, even though we may not be expert in stock market trading, we can be expert in the statistics of the numbers that are being gathered. Okay, so for example, we might say, oh, finally the stock price has kind of achieved a breakthrough. Why? Why do you say that? Oh, well, because the Z-score is now 4.2. And why is that so exciting? Because we know for sure that any set of data, not just stock price, but any set of data, when it exceeds 3 as a Z-score in absolute magnitude, it's an outlier. Now, I'm not saying outlier in a positive way or negative way. As I said, it can be noise, as those market flash crash, right? Because algorithms miscalculated. So for a moment, it kind of like short to zero. Oh, let me sell at $0, and then suddenly the market crashes, right? And that is just that's an outlier, but sort of kind of a noise that is not interesting. But when there is a government announcement that we didn't hear about, but local stock prices are beginning to react to it, then we notice the number shot up for good reasons. And while we might talk about the reasons, and that would be domain expertise, we are wondering if this is something interesting, right? So what do you mean by interesting? This is what we mean by interesting. Yeah. So Z-score will almost for sure break through magnitude 3. So plus 3.5 or minus 4.1, right? That will show something as an outlier. And the expertise part, the domain expertise part, come in terms of interpreting. Is this outlier a good thing or a bad thing? So that requires a bit of know-how and knowledge and domain expertise. So if you have that, that's great. But as long as we are studying statistics, we need a way to talk about outliers. Okay, something interesting or something noisy has occurred. What is that? And Z-score provides this mechanism. So that's why it's so interesting to convert data to Z-score just to have a look. Yeah. So if you're doing, just a side note, if you're doing programming, robotics, vision, audio, AI, you might want to sort of let that robot know about what is bizarre, what is interesting, right? Interesting will be not the norm. The norm means the Z-scores are all within plus minus 3. And not the norm, outliers, interesting, or else disturbing, or else noise. Please discard those extreme noise. However you interpret them, the robot has to react to that disturbance. So when should the robot react? Detect when the Z-score goes beyond plus minus 3. That will be one way, right? So again, just to give you some idea why we are so interested in having Z-score.